So this goes with HMH textbook lesson 15.5. Your essential question, how does the graph of f of x equals ab to the x power? So right here I wrote this, this is the symbol you get when you do shift 6. So sometimes you don't always have the ability to write an exponent, and that's one way to show an exponent, okay? A times b to the power of x, that's what that means. So how does that change when a and b are changed? Your learning goals is I can graph an exponential function still. Good morning, Karan. Good morning, Gian. Good morning, Isabella. Okay, so a little bit of review from this week. We looked at exponential functions, and this is the basic form of an exponential function right here. Y equals a times b to the power of x. And so some different things will happen to your graph depending on the values of a and b. If a is greater than 0 and b is greater than 1, you're going to get a graph that looks like this. If a is less than 0 and b is greater than 1, then your graph gets reflected over the x-axis, okay? And then if a is greater than 0 and b is less than 1 but also greater than 0, so b is a proper fraction, what would happen is your regular looking graph here would then get reflected over the y-axis. And if a is less than 0 and b is less than 1 but greater than 0, and they have little examples here to show you what we're talking about, what that would look like, then you would get something like this. Okay, so it's actually done both reflections that you see here for these two. Okay, so it's taken this original one, it's reflected it over the y-axis and over the x-axis. Okay, so these are just some ways to recognize what the graph would look like depending on how the a and b change. As we work with exponential functions, Desmos's graphing calculator should really be like your BFF with this stuff because it is so useful and you can use it, and I want you to use it, okay? So don't rely on doing everything by hand when it comes to graphing things. Get used to using the Desmos graphing calculator, all right? And we are going to be using that today, okay? So some vocabulary here. You know, we can also have things happen to our graph, such as a stretch or compression. And so looking at what a vertical stretch is and a vertical compression, there's some pictures here to go with that. So your graph could also change in different ways. So if you have a vertical stretch, that's a transformation that pulls the graph away from the x-axis. Okay, and so over here in this picture, f of x is the parent function. That's what we call the function we start with before a transformation, before we change it. And g of x is the translation. So a vertical stretch, if I started with f of x and then I did something to this graph, I changed it, and now I have a vertical stretch, it looks like g of x because it's now moved away from the x-axis, okay? And so basically what has been done here is we multiply the y value of each xy pair by a, where a, the absolute value of a, is greater than 1. So that would then stretch your graph by a factor of the absolute value of a. Right here, the y-intercept of f of x is +1, and the new y-intercept is +3. So this is a picture where the parent function has been multiplied by a factor of a, where a is 3. Okay, and it stretched it. You could also have the opposite, which is a compression, a vertical compression. Okay, so we can like squish this graph down. Basically, it's a transformation that pushes the graph towards the x-axis. Okay, so in this case, y equals 1 and 5/10 to the x power. This here is the parent function. And then the new one after, we multiplied it by a number here, 0.3, which is actually less than 1. Its absolute value is less than 1. And so that's why it got shorter and pushes it towards the x-axis, is closer to the x-axis, right? Where a is 0.3 in this case. All right, so you can also have, just like vertical stretches and compressions, you can have horizontal stretches and compressions too. Okay, I didn't give you the definitions of those, but it's the same idea, except, you know, now we're going horizontally, side to side. And when we have a horizontal stretch or compression, it's the value of B that's actually changing. So this slide right here, this is a table that just kind of covers all the different ways your exponential function could change. And what you're seeing here is an introduction to this stuff, okay, because this also works with linear equations, which are straight lines. It works with quadratic equations, which we're going to look at soon. It also works with polynomial functions. All right, so you see this as you move on in math. This is something that repeats. This is a basic idea that you're going to see a lot. Okay, so all these transformations is the same basic idea here. Again, your parent function, what an exponential function always looks like is you have f of x equals a times b to the power of x. All right, and depending on how we can change this, these different things will happen here. So when you were in 8th grade, you were supposed to learn about transformations, and there's a good chance you didn't learn about transformations last year. So a transformation, if you imagine something in the coordinate plane, it could be a line, it could be a point, it could be a star, it could be some like two-dimensional shape, a square. Okay, so there's different types of transformations. So one of those is called a translation, okay? And so translation means you're sliding an image or a point or a line. You're sliding it either left to right, or you're sliding it up or down, okay? And so a vertical translation or a horizontal translation, a vertical translation means you're sliding something up or down. And a horizontal translation means you're sliding something to the left or to the right. And so the way that gets represented with your function is you would then be taking the parent function f of x and then adding a number here, okay, for a vertical translation. And depending on if this number here that you're adding is greater than 0 or less than 0, would depend if it moves up or down, all right? And so here is where I'm going to come over to Desmos and just kind of show you. Let's start with the parent function. I'm going to use this one that they gave us here, all right? I'm going to use y equals 3 times 2 to the power of x. And when you're in Desmos and you want to get the power of x, a shortcut is to use Shift 6. And that's going to move your cursor up to where the exponent would be, and then you can type your exponent there. Translation and transformation are also biology term. It's going to get confusing. So in biology, when something transforms, it changes. So you should actually use that idea as to help you remember what it means in math. A transformation in math just means something is changing. What does a translation in biology mean? When genes are decoded. Oh, okay. So they, it's like translating like with language almost, right? So you can think of math terms and think about other ways. Angel, don't be like that, okay? So it's good to make these associations because it's going to help you learn the vocabulary better. If you translate language, you take it from one thing and you change it to something else. Translating genes, okay, they're decoded in the ribosome. All right, I don't know what that means exactly, but you know, try to like think of it. A translation here is it's changing, it's sliding either to the left, the right, up, or down, or it could do both. It could go left and it could go up. It could go to the right and it could go down. All right, so if I want to change this parent function here, I'm going to write it again, but this time I choose f of x. Okay, it doesn't matter. It looks exactly the same. If I type y or f of x, it looks exactly the same. They're interchangeable, but we use f of x when we have function notation. Okay, and if I want to differentiate this f of x from this f of x, I could actually change this to g of x or h of x or any other letter I want, or I could keep it as f and then do a subscript, which is a lower number, and Desmos will just automatically recognize if I type a 1 right now, it's going to drop down. So to make that 1 go low, I didn't have to do anything. It just knows that I'm in function notation, and it would drop down as a subscript. Okay, and so I want to change this parent function that's in red. I want to change it. I'm going to show you what a vertical translation looks like. So what that means is I have my original function, and then I want to come out of that exponent. You would just arrow to the right to come out of your exponent. And I'm going to add a value here. If I add a value of k that is greater than 1, it's going to shift up. So if I add 5, now my blue graph is the same as the red graph, but it's shifted up. It's slid. It's a translation vertical up. If I change this to a negative 6, it's going to slide down. All right, so these are just rules that, you know, it shows you how things can change. Horizontal translation, so f of x minus h here, it's actually changing the value of x this time. All right, so I'm going to leave this here. I'm just going to turn off the graph. You can decide which ones you can see at any time. And now I'm going to change my parent graph again. Okay, so I started with this. If I control copy paste, yeah, that's a lot easier. All right, and so the green one is here. If I turn it off, you can see the red. If I turn it on, you see the green. Right now it's exactly the same, but let's see what a horizontal translation looks like. And so it changes my value of x to minus h. So here, and I do need to go up to the exponent. If you want to, this is something I noticed with Desmos. So like I want to change my exponent value, I need to put parentheses up here around the x, because otherwise it's going to drop me back down to just like working on like not in the exponent. So if I put parentheses around the x, now I can change what x is. All right. And so it would be subtracting a value. If I subtract a number that is greater than 0, if I subtract 7, it just went to the right. If I subtract a number, and again, I have another set of parentheses in my parentheses, that is less than 0, like negative 3, it shifts to the left. Okay, and so that's all this one does. It's just shifting left to right. This one shifts up or down, depending on the value here. Okay, so I'm just showing you what these different things look like. Here's another type of transformation called a reflection. And again, you want to think about what a reflection is outside of math. Think about the word reflection. Think about like if you look in a mirror, your reflection is the same image, but it's somewhere else. Okay, so a reflection has a like an image line, a mirror image line. And so you can see here, there's already an example. F of x is the parent function and g of x is the translation. So f of x is here and g of x has then been reflected and also compressed. So there's two things happening, but just the reflection part, I'll show you that. So let's start again with our parent function. Use that here. Now it's in purple. And this time I want to reflect it across the x-axis. So negative f of x, which means the entire thing is negative. But I put the negative over here in front of the 3. and it just reflected across the x-axis. If I want to see it reflect across the y-axis, then my negative needs to go where the x is, up here. And I'm not sure if I need parentheses. No, I didn't need parentheses. And so that's showing it reflecting across that way. So you could turn that off and on. We have vertical stretches and compressions and horizontal stretches and compressions. Okay, so we kind of saw these ones already back here on this page. So I'm not going to keep doing this with you. All right, but there are some pictures here, some examples. You can open up Desmos and play around and look at what these different things do to any function that you start with. It'll change it in a certain way, and these kind of basic rules follow through with linear, quadratic, polynomial functions also. All right, we are on the last slide here. So I am going to open up Desmos for all of you right now. I'm just going to force open a tab. If you already have it open, then you can just close it. But I'm sending you the Desmos graphing calculator. Okay, and you're going to use your graphing calculator to answer these questions. And so what that means is that you can come in here and you can clear all these out just by Xing out any function you have. It gives you a clean slate. For exercises 1 and 2, refer to the functions f sub 1 of x is equal to 2 and 5/10 to the x power, and f sub 2 of x is equal to 3 to the x power. So we have two functions of x, and they're differentiating them with a subscript. So when you start typing, if I type f, I don't have to do anything to get the 1 to go down as a subscript. I just type 1 normally, and it'll automatically go down. And then my cursor will come back up, and I could use an open parenthesis x, close parenthesis, equals, type 2.5. And now to get my exponent of x, you have two choices. You can use the shortcut on the keyboard, which is Shift-6, or show the keyboard and click the button a to the b power. Both ways work, and then you can write your exponent. You need to type in both functions. Now we have f sub 2. F2 automatically goes down. Open parenthesis x, close parenthesis x, equals 3 to the x power. So you can do Shift-6, and I'll take your cursor up, or the a to the b power. All right. And then you'll have two pictures, or two graphs on your coordinate plane. It's hard to see what's happening. So what you want to do is zoom with the plus sign into where you can see a little better of what's going on. Okay, so I'm going to give you a few minutes right now. I just need you guys to type in these two functions on the Desmos graphing calculator, and then we'll answer these questions 1 and 2 together. All right, but let me give you some time just to get them typed in. All right, maybe 3 minutes. So type in your functions. You have 3 minutes to get that done. You may have like a split screen where I can't tell, but some of you are still in the Google Meet. I want you to go over to your graphing calculator tab that I opened for you, and I want you to put in both of these functions. Okay, I want you to practice typing them in. The subscript will show up by itself. You just type like normal, and it'll automatically drop down. The exponent, you're going to have to either use this button here, the a to the b power, or Shift-6. Another minute and a half. Just get these two functions typed in, and then we'll answer 1 and 2 together. And if you have them already typed in and you're just waiting, you could always play around with like the different features in Desmos. So if you are done typing them in, if you come back to the Google Meet, I'll just show you real quick. If you wanted to change the color of your graph, you would go up to Settings, which is the little wheel. And if you click that, it's going to bring it up so you can change things. If you click on the color now, say I didn't want it to be red, I wanted it to be green, and I didn't want blue, I wanted purple. Okay, you can change the color of them and then say done. You can zoom in, zoom out. You can go home, which is like a default zoom. Right, you can save any graph that you're working on. I've showed you guys this before. It's been a long time since we've saved any graphs on Desmos. That was back when we were working in statistics in the first semester, first triad, I think. So you can always save a picture of your graph if you wanted to by clicking save. You can open up past graphs. And I still have, look at that, I still have all the box plots and dot plots and histograms saved from when we were doing, when we were doing statistics. That's funny. All right, so let's look at how we can answer 1 and 2 together. Question 1 says, which function grows faster as x increases towards 0? So as x increases, why did I say 0? I'm sorry. As x increases towards infinity, that means, and I'm going to draw a picture here, that means as x goes this way, nope, way too big of a line, besides that. All right, as x goes this way, this is towards positive infinity. All right, as you move along the x-axis in the positive infinity direction. What function, which function is growing faster? So what you want to do is look on the side of the side of the y-axis where x is moving towards infinity, towards the right. Which one is always above the other one? The purple one, right? The green one is never above the purple one. The purple one's always above it. Doesn't matter how far out I go. The purple one is always moving faster than the green one. And so the purple one on my graph is f sub 2 of x. And so that's what I'm going to write here, f sub 2 of x. You know, as you try to type this stuff, it's a little tricky. You can type it as, I mean, paired x not real nice, but I could do f, and then leave a space for the little 2, and then do open and x and close parenthesis like this. And then go back with the pencil tool and then add the 2. Like that. I can do it that way, although I don't want that to be green because that's confusing. Okay, you don't have to write the whole thing. So f sub 2 of x, that's talking about the second function. And now we're going to look at the second question. Which function approaches 0 faster as x decreases towards negative infinity? Negative infinity. So negative infinity is moving along the x-axis to the left. That's how you get to negative infinity. and I'm trying to figure out which function approaches 0 faster. So again, come over to your graph where you have them both at, and we're going to look at the side of the y-axis where x is approaching negative infinity. Which of the two functions is always going to be closer to 0? So it's getting to 0 faster. F2 again. Yeah, it is F2 again. Okay, it's the purple one on my screen. Okay, because it's always closer to 0. It's always closer than the green one at any value of x. If x is -2, which one's closer to 0? The purple one. If x is -1, which one's closer to 0? The purple one. If x is, and now see, as you go out here, you can't really see, but you could zoom in. You can play around with the zoom. It looks like they're getting really, really close to 0. So over here at -8 and 77/100. The purple one's closer to 0. It's never going to touch 0, weirdly enough, but it'll get infinitely close to it. If you do play around with your zoom and you want to go back, just hit default zoom, the home button, and it'll take you back. So again, we're going to write that F sub 2 is the answer. On what we just did for number 1 and number 2. We're predicting end behavior of functions. That's what we're doing. We're going to move on to 3 and 4. Okay, so I'm going to give you guys 5 minutes to do 3 and 4. We have that long, we're good. So 5 minutes to do number 3 and number 4. What you should have when you graph these two functions, f sub 1 of x is that, f sub 2 of x is this. You may have different colors, and so your picture should generally look like mine right here. Maybe you have different colors, and depending on what level of zoom you're on, it might look a little bit different. If I zoom out, okay, you don't see as much as when you zoom in. Let's see what we came up with for number 3 and 4. So I got 9 of you to respond. F sub 1, F sub 1, good. F sub 1, good. F sub 1, F sub 1, perfect. So those of you that have answered so far, you're correct. Which function grows faster as x decreases towards negative infinity? So these questions are not exactly the same. But they're asking you basically the same stuff, but they're asking you about negative infinity first, all right? So as we move to the left towards negative infinity, which one is growing faster? So if I'm just looking to the left of the y-axis, which one is always above the other one? Which one, no matter which point of x I choose, if x is -1, which one's closer to infinity? The green one. If x is -4, which one's closer to infinity? Way up here, the green one. Okay, so it's always my green one, which is the first one, f sub 1 of x. Which function approaches 0 faster as x increases towards positive infinity? All right, so now we're looking at moving to the right, going towards positive infinity. You can just say infinity. You don't have to say positive infinity, but that's stuff. Okay, so that's when we're on the right-hand side of the y-axis. As we move to the right, any value of x I look at, if x is 1, which one's closer to 0? The green one. If x is 4, which one's closer to 0? The green one. The green one is my first one, f sub 1 of x. Okay. For the last two questions here, 5 and 6 says label each of the following functions. G of x as a vertical stretch or vertical compression of the parent function f of x, and tell whether it is reflected about the x-axis. You have two ways you can do this. You can type in both of these to see what it looks like, or you can go back to right here and just use these rules to see what would happen. So that's the last thing you're going to be doing here, 5 and 6. We are getting close to the end of class. So I'll do the first one with you, and then you can do the second one. How about that? First one here, I'm going to type this in up here, g of x. Is 0.7, open parenthesis, 0.5, close parenthesis, shift 6 to the power of x. All right, there's my first equation. So the parent function is f of x. G of x is the transformation. So the parent function, f of x, you have to make sure you're comparing them in the right order. Okay, so the parent one is the one you start with. And there's, so the red one's the parent one for me. And I think I could drag them around. To me, it makes more sense to type the parent one first. And you can do that by dragging just the red dot. You can change their order, or the black dot, whatever color dot you have. Okay, so question says, is it a vertical stretch or a vertical compression? So G, if I compare it to the red one, has gotten closer to 0. That's a vertical compression. It's gotten closer to the x-axis. So this is a vertical compression. And then the other question, it says, is it reflected about the x-axis? Well, the x-axis is here. I don't see my g of x being down here as an image, a mirror image down here. It's not. Okay. If I had a negative here, it would be, but I don't. So, no reflection. Right? So you're going to do the same thing for number 6. Type in g of x, type in f of x, or just use the rules on the previous slides to figure out, is it a vertical stretch or vertical compression of f of x? And is it reflected about the x-axis? So there's shortcuts to figuring it out, or you can use Desmos and just look at it, right? Your choice, how you want to do that.